Thank you for joining us for today's webinar hosted by IEEE. My name is Dr. Shelly Gandhi from CEPT Research and Development Foundation. We are happy to have you all here for our webinar on the topic Scatterometry, Winds, Vegetation and Ice, Dr. David. IEEE GRS's Gujarat chapter was formed May 2013 by Dr. Shiv Mohan, who is founding chair and India's GRS's listener. The chapter has about 60 members representing various institutions of Gujarat. Chapter is among the who initiate its newsletter, website, and host a number of activities with global experts, leaders, speakers, and conferences. In this year, due to pandemic, we will be conducting all our activities virtually. Among various activities, we are planning international science and remote sensing TLP competitions and many more. This lecture is a part of our webinar series. Just a little bit of housekeeping before we get started. All the audience will be muted during the presentation. Our presenter will speak for about 40 minutes and then we will open up the floor for questions. If you have any questions, please type them in the question box in your GoToWebinar control panel, and these will be selected and answered out after the presentation. We will record the webinar and upload it for future reference along with the presentation. I would now like to request Dr. Shiv Mohan to introduce our speaker for the day.
Okay, good evening to all of you. It is my pleasure to introduce a well-reputed scientist, a global scientist who has contributed a deal in radar remote sensing and especially the scatterometry. And I am really happy to have him in our chapters activity, which we are trying since long. And he will be himself introducing through first few slides. That's why I understood it while I talked to him yesterday. So I straightforward welcome him and I request him to start his presentation. Thank you.
Thank you all. And I'm grateful for the opportunity that I have to sort of visit with all of you and talk about some of the research that I and some of my students have been doing for the last few years. So I've got a slide up in here running, and I hope everyone can see the slide okay and understand my English accent. I am from Brigham Young University in Utah in the United States, and I've been a professor there for over 30 years, where I specialize in remote sensing. Before I came to BYU, where I work now, I used to work for NASA's Jet Propulsion Laboratory, where I worked on radar remote sensing systems, primarily scatterometers. So some of this work derives from some of that original work. Now, when I used to work for NASA, when all the important VIPs, the important people would come to visit, we would put on our ties and our jackets, and we would put on what we called a dog and pony show, the fancy slides and all this sort of thing. Since I consider all of you very important people, I thought it'd be good for me to start out with a dog and pony show. My wife and I raise miniature horses. These are very small horses. The taller one here in the back is the mother of this one in front, who I can actually carry around. And we've got a little dog to go with it. Now, to begin with, let me just start very basic. What is remote sensing? Remote sensing is seeing at a distance. And all of you are already experts in remote sensing because you use your eyes, which operate at optical frequencies. Now we have modern technology like cameras and telescopes and radar, so we can do remote sensing from a distance. So this is where I'm from in the United States, in Utah. Now, remote sensing, we start off looking far away And as we move closer, the pictures that we see start to have more and more detail until finally we get to the view that we as humans can see. All that sensing happens at the optical wavelengths where we see color on the electromagnetic spectrum. Well, there's a large part of the electromagnetic spectrum, and I like to work in the microwave regions. Why? Because I can show you the wavelength of the electromagnetic signal with my hands, and it's not so small or so long that I can't do that. Now, microwave remote sensing is another way of seeing the world, and it has certain advantages over other ways of seeing it, including that we can see different properties of the surface at different frequencies. And we can operate at night because we can provide our own illumination. Now, microwave remote sensing, we can split into active, that's radar, or passive radiometers, radiometry. And there are different kinds of radars in those two types. We're going to talk today primarily about active radars and about scatterometers. A scatterometer is an instrument that measures the scattering, backscattering usually, from a natural surface. Now the idea is that we transmit a signal toward the surface and we measure the reflected signal coming back. This allows us to see the surface in a way, kind of like a flash camera, to see more things, okay? The advantages and disadvantages are that the signal is coherent. Coherent means we can do fancy processing with it, but it also means we have to deal with speckle and fading effects, okay? I'm sort of preaching to the choir on this, but when we look at the radar, these classes, splitting them up, a little more detailed, the key thing that scatterometers offer is a very highly calibrated. That means it's stable. The resolution is not great, but it's very, very stable. That's in contrast to, say, a synthetic aperture radar, which is a very high resolution sensor, and although it's reasonably well calibrated, it doesn't offer the same kind of precision that we can get out of a scatterometer. Now, radars can measure three main things: time delay, Doppler shift, and reflected power. Okay, they can also do it at different polarizations, at different frequencies, and offer different geometries. The basis of scatterometry is the radar equation, where we transmit a signal through an antenna. It goes there and back, so we get a two-way or a gain squared. The wavelength, the area of the footprint that the antenna illuminates, all divided by the range to the fourth power. The last parameter here is sigma naught, or the radar cross-section, or the normalized radar cross-section, which is a physical property of the surface, and that's what we are interested in measuring. Unfortunately, the measurements we make are also noisy, so we have to deal with noise in the observations. The radar we send bounces off the surface, and the amount we get back depends on the dielectric constant, the permittivity of the surface, as well as the roughness. Now, this combination of permittivity and roughness gives scatterometry both its power and its weakness, because I have to separate the two. From a very flat surface, the radar signal goes down and bounces away from the radar. But as the surface becomes rougher, more of the signal bounces back toward the surface, and I see more information. Well, we can also see through forest canopies, which are very rough, through soils and very dry deserts. Urban areas offer a special challenge because the backscatter gets a corner reflector effect, which tends to make the signal very bright in urban areas. And we'll see that in some of the images that I show. Now, over the ocean can be very smooth and flat. In this case, we get very little reflection because it bounces away from us. As we add a little bit of roughness, the scattering is mostly in that main direction, but goes in some other directions as well. So this sort of shows the pattern. As the surface gets very rough, we get a Lambertian scatter, which means it gets scattered in all directions. Now, sometimes surfaces can be modeled as a very large scale roughness, so we can use sort of a flat facet model. on which we superimpose a slightly rough surface. So we see a combination of effects. That's the important thing that we deal with in scatterometry. In general, the signal backscattered from the surface, its backscatter, the amount of power coming back, is very low when I'm looking straight at the surface, when the incidence angle is small. And as I go into higher incidence angle, in other words, I look from straight down to off the angle, I get into the rough scattering regime or characteristics. Now, the details of this depend on the surface, but this is the general idea. As I change the surface roughness from very smooth to very rough, this peak drops and the roughness scale comes up. The backscatter is the amount of signal that we do. Now, most scatterometers operate in this regime, in this part of the incidence angle. When in this incidence angle range, the roughness is one of the primary things we're measuring, but the dielectric constant, the surface permittivity, also plays a role in how high this curve is. Now, when we look at the Earth's surface with a radar, these are images of the Earth's surface, just the land surfaces and the ice surfaces, as seen by a 14 gigahertz radar. These were collected by the NASA Scatterometer, which was launched back in 1996 and collected data over the Earth's surface. This sensor was actually designed to measure the ocean, and we'll talk about that. But as we look at the land, we see some very interesting features. Rainforests are very bright, deserts are very dark, and ice is particularly interesting in this. So we can extract geophysical information about the environment from these images. Over the ocean, we get an effect known as Bragg resonant scattering, where the scattering is enhanced or brighter when I look up or downwind across the troughs of the ocean. And when I look down the troughs, the scattering is reduced. So I get a sinusoidal variation in the backscatter with direction of wind. That allows me to extract wind direction as well as wind speed from the scattering measurement. So here I've got an example of that behavior. This shows the radar backscatter in decibels, in dB, versus the angle of the wind compared to the radar look direction. Okay, at higher wind speeds, this curve is a little flatter, but we still see a modulation of the backscatter versus wind direction. And as I change the speed, this modulation gets higher at lower wind speed, but the total return from the surface drops. So if I take measurements from different directions, I can infer the wind speed and the wind direction. Now the scattering is occurring from very small waves. So up in this picture of the surface waves, we can see large scale waves. Those are called swell. And there's some smaller waves riding on the surface. Those are known as capillary waves or capillary gravity waves. The scatterometer is actually resonantly scattering off those small waves, but as the large waves tilt the surface, they affect the scattering from this. Now, there are two major classes of spaceborne scatterometers that have flown. Fan beam scatterometers, which illuminate the surface with long, thin antennas that produce long, thin patterns on the surface of the Earth. That's on the left. The Americans and the Europeans have primarily used fan beam scatterometers. They're the only folks. And then there's a rotating antenna that uses a pencil beam that points the beam in a very focused direction that rotates around the surface. The Americans first did a pencil beam scatterometer, conically scanning one. This was followed by two Indian scatterometers, which are really cool. The ocean scatterometers, and those are very nice. And now the Chinese have orbited both a conically scanning scatter and then a hybrid where they rotate a rotating fan beam antenna. I'm primarily going to look at the scanning scatterometer, which I will emphasize the sea wind scatterometer because most of my experience in designing scatterometers was for that one, and also for the NASA scatterometer. But since this one also applies to the Indian scatterometer, I'm very partial to that particular design. Now, here's the actual timeline of all the history of some of the scatterometers, and I failed to put the second scatterometer from India down here, and I apologize. But it shows how we went from 2 fan beams to 4, 2 on each side of the spacecraft, to 3, to then NASA scatterometer, then eventually ASCAT, then we've got sea winds and the various OSCATs, and now the Chinese scatterometers. Why do we fly this thing? Well, this movie that you're seeing represents one day as a hurricane, a typhoon in the Atlantic Ocean, we call them hurricanes, crosses from the Atlantic Ocean onto the coast of the United States and South Carolina. And as it does, we can see the eye of the storm crossing the outer Grand Banks off the east coast of the United States. These images of these clouds are wonderful. They tell us a lot of structure, but the damage that the storm does is at the surface. For this, we want to know what the winds are doing. So here is a map of the winds, of the surface winds, as measured by the scatterometer, the sea wind scatterometers that flew over. And there is a wind vector showing the wind speed and the wind direction every 25 kilometers. The meteorologists were ecstatic. They could see the high winds right as this hurricane crossed onto the surface. Okay, this is great. In fact, they almost have so much data they don't know what to do with it. Well, as I left NASA JPL and came to Brigham Young University, my students and I realized we could use the scatterometer for more than just looking at the ocean. We could look at land, but we also realized we could do some fancy digital signal processing to improve the effective resolution of the data. And so here is a zoom-in view of that scatterometer, that same data, as it passed right on the coast using our enhanced resolution technique. Now the black little wind barb flags represent the original 25-kilometer resolution data. We've done the signal processing to enhance them and create finer resolution. We can now resolve the eye of the hurricane, and we can get much closer to the coast and get a better understanding of what's going on. So this is kind of the future of scatterometry when we look at very high winds, typhoons and hurricanes, when we want to understand the details of the storm. So here's an example of a global scatterometer view of winds over the ocean. And we can see a major hurricane out here in the Atlantic. It's actually the same one I just showed. Here's that sort of an animation of that. We can see a major storm, another cyclone down in the southern hemisphere. And now we see both the land and the ocean. So we have winds over the ocean and the backscatter of the ocean. So we see the tropical rainforest over here and the Sahara Desert. Now, as we look at some of the applications of scatterometry, the main one, of course, is to do wind observations. So we can do typhoon and hurricane tracking. And because the United States gets hit by a lot of typhoons and hurricanes, I started working with the U.S. National Weather Service, NOAA, National Oceanic and Atmospheric Administration, to create tracks for all the hurricanes that strike the United States. So we used all the various scatterometers and tracked them, generating conventional resolution images of each storm. This is Katrina, which did a lot of damage in the United States back in 2004 or 5, whenever that was. And this is a high resolution view. We were able to use the high resolution view, resolve much finer features than is possible with conventional storms. And we've begun to do this same sort of thing with the Indian scatterometers as well, because they're so similar to the sea wind scatterometer. So we kind of zoom in here, and here's the regular conventional view right as it's about ready to hit New Orleans. And the high resolution view, you can see the extremely high winds that occur in the center. They are so high, we've got a lot of rain in there, so we get some contamination. We'll talk about wind and rain just in a few minutes. Tracks of the scatterometer typhoons as they move across the Atlantic Ocean. Now, one of the things that we do, we realize that rain adversely affects the scatterometer backscatter. It does this in two ways. One, we get backscattering from the raindrops. Two, the raindrops modify the surface of the ocean. Falling rain tends to suppress the very small waves that the scatterometer is most sensitive to. So what happens is the scatterometers measure the wrong wind speed, either too high because there's too much return from the rain effects, or not enough of the wind direction information. So my students and I developed techniques for simultaneously retrieving wind and rain by using model functions that combine the wind and rain to retrieve them both. And so as we began to do that, we could retrieve where the wind is. So this is a quick scan observation of a storm front that includes a lot of rain. And it says, well, there's a huge amount of wind there. But in fact, the actual background wind field is only 10 or 12 meters per second. This is mostly the rain. We have a co-located tropical rain mapping mission precipitation radar path, a Japanese instrument that's operating up there, that measured this rain field. So we applied our simultaneous rain retrieval and extracted the rain rate. And we're able then to get the wind speed, finding out, hey, the wind speed is not that large up there, as we would expect. That's mostly a rain signal. So now we have an instrument that can measure not only winds and wind speed and wind direction, but also rain rate. Again, the Indian scatterometers work just fine on this. We use the same model function. So here's a particularly interesting example. This is the Hawaiian Islands in the Pacific Ocean. You can see the land here, the dark. The gray areas here are areas that we have to mask out of the image because land is a very bright backscatter and it contaminates the wind retrieval process. So we've developed techniques to remove them. And here we have a very bright high wind event, but it's not high wind because it's a thunderstorm. So the high resolution allows us to identify that very clearly, and we can see, we can understand that is not some intense wind, it's actually a rain event. Now, oil on the surface of the ocean can also modify the backscatter by suppressing the high frequencies, the small waves on the surface. Okay, so here is a C-band observation from ASCAT, from the European Scatterometer, of the Deep Horizons oil spill in the Gulf of Mexico. So here is the New Orleans area I showed you in Hurricane Katrina, and this terrible oil spill is right there. And this big patch of oil is changing it. So the backscatter is very dark because there is no backscatter. There's no waves to scatter off of. So we were able to track this event in real time and be able to map where this was and provide a new application, Scatterometer, to detect oil slicks. Now, admittedly, at the resolution of the scatterometer, which is very coarse, a few kilometer pixels, oil spills normally aren't that big, thank goodness. But when they're very large, the scatterometer can be very effective. When they're smaller, we can use synthetic aperture radar. Now, we also started looking at the possibility of, can we measure ice? This is an animation, a sequence of images, high resolution images of the backscatter from sea winds as the surface of the Great Lakes froze over. So you're seeing one image for each day over a sequence of days. And when the lakes usually show up dark compared to the brighter backscatter of the land, but as ice forms on the surface of these lakes, you can see this cloudiness appear due to the backscatter from the sea ice. I also point out that the urban areas such as Chicago and Minneapolis and things like that, and Detroit and other areas show up very bright in these images because of the backscatter effect. The change in the backscatter is some of the areas go from light to dark over the land are a result of freezing and thawing events. Again, we see, hey, there's a lot of information in scatterometer data if we can just exploit that information. I've got to tell you a quick story, a fun one. This is the very first image that we made from the first sea winds data that was collected in 1999. And this was over Antarctica. So the bright center area is the continent of Antarctica in the Southern Ocean. Around the outside is sea ice, and there's the ocean outside where we do the wind. Well, when we made this picture, we noticed that there was an extra bright dot out here. This is a giant tabular iceberg that broke off of the continent of Antarctica down here, floated around in the ocean until it came up into a shipping lane near the Drake Passage. The other bright dots are islands. There's another iceberg there. I was curious about the name of this iceberg because large icebergs get named by the International Ice Patrol. And so I called them to ask them, and there was a flurry of activity and noise, and you could hear what was going on and people talking. A few minutes later, they came and says, "That's an iceberg. That's B10A. We were tracking that, and due to cloud cover, we lost track of it. Didn't know where it was for 4 months. And the last time where we knew it was clear down 1,000 miles south. You found a lost iceberg." Well, here is an optical picture of an iceberg, not the same one, taken from the space station. In fact, my students have to provide iceberg reports to the astronauts on the space station because one of their hobbies is taking pictures of these things. And it shows one of these icebergs that's 25 miles long by 12 miles wide. And you can see the little pieces that break up. Some of them are 1/2 kilometer in size. And this one up here is 2 or 3 kilometers in size. Here's a picture of that iceberg. It's taken from a ship. We use the scatterometer data to help the ship navigate to this iceberg. 9/10 of an iceberg is below the surface of the ocean. So it's 600 feet deep and it extends 60 feet off the surface. This represents thousands of years of accumulation of snow in Antarctica. Okay, we only have one picture of that giant iceberg B10A that cracked off of Antarctica, and that's shown here on the left. And you can see that even with changing the colors in the image to make it easier to see, it's very difficult to see the iceberg against the cloud. Well, down in the lower right-hand quadrant of that iceberg, I blew up a corner of that, and you can see the little dandruff, the little white specks coming off. Those are 1/2 kilometer icebergs. These icebergs in Antarctica are enormous. They are huge. This is a scatterometer image movie that shows the movement of B10A and another iceberg that we did know where it was, A22B, with 1 image per day back in 1999 and the year 2000. And you can see how quickly these icebergs move. Someone compared them to paramecium, little bacteria swimming around on a microscope slide. You can also see the continent of Antarctica off to the right and the melting and the thawing of sea ice around the continent. And you can see the growth of that sea ice moves out and moves in response to the wind. The ghosty effect around the outside represents the movement of storms and winds out over the ocean. That's what the scatterometer is actually designed to change. The reason it flickers and moves so much is because the wind changes from day to day, from past to past so much. The land, the ice, does not change so rapidly. This is a cool application. So as a result of this, BYU started tracking all the icebergs, and we are now one of the largest databases of icebergs in the world that you can download from our website. Here's another movie that shows some other icebergs that you can see in that, and this is a really nice feature. We started providing this data to the International Ice Patrol so they can track icebergs and use them for both research and to help with navigation, because you can see how they move up into the Southern Ocean. This is in the Atlantic. This also happens in the Pacific. Okay, well, as we collected this database, we noticed that the number of icebergs is recorded by the Iceberg Patrol in the United States, that's the National Ice Center, had this huge increase going from the 1980s up into the 2000s. People wondered, since the number of icebergs are increasing, is this some sort of sign of global warming? We decided to investigate this question. So we went back and looked at all the scatterometers that have flown for the last 20 years, beginning with the CSAT scatterometer known as SAS. The very first radar observations were made by SAS back in 1978, and it showed there were a lot more icebergs present around Antarctica than they had counted. Now, when we flew the next scatterometer, which is the ERS-1 and the NASA scatterometer, we found out there were a lot of icebergs, and then there really was an increase. Well, this increase in the count of the icebergs at the National Ice Center was due to their improved technologies. They went from ship reports to the first satellites to finally using scatterometer data, and they started to track the data much better. These two events in 1999 and in 2002, where the icebergs suddenly increased, were major calving events. Okay, a calving event is when a chunk of an iceberg breaks off the end of a glacier, and it gradually breaks up into smaller icebergs. These events, the calving events, occur about every 50 or 60 years from the Ross and the Ronne ice shelf. And the last time they occurred was about 50 or 60 years ago. So these two major calving events are what we normally expect. So the apparent increase in icebergs that occurred in the early years was really only the increase in our ability to track the icebergs. In reality, there wasn't a big change. So we concluded that we can't use the number of icebergs as a sign of global warming. Okay? However, when we go back and look at Greenland and Antarctica, we'll see evidence that scatterometers do reveal that. So, since we made such cool pictures of Antarctica, let's go back and look at them a little further. This is a C-band, that's at 5.4 gigahertz, and Ku band, that's at 14 gigahertz, images of Antarctica taken with a European scatterometer and an American scatterometer, that's QuickScat. And we can see a lot of beautiful features of both the land and the sea ice around it, okay? When we combine those into a false color image, we can see some of the beautiful features that are present in the scatterometer data. Icebergs and areas that refreeze, ice sheets, show up as very light. That means you get a lot of backscatter, and that's because the radar signal penetrates the snow and bounces off the layers and layers of snow in there, and also frozen ice bodies that occur when the water starts to melt, percolates down into the snow, and refreezes. The big areas that don't melt show up as this beautiful golden color. The purple areas are where we get different scattering roughnesses from the sea ice. Okay, and then the ocean, which is the lower backscatter compared to the ice, shows up with this beautiful blues and purples and greens. Let's move, too cold down there, let's move to where it's warm. So this is in the Amazon rainforest. The light area represents the jungle areas, whoops, whereas the darker areas represent savanna. So we compared backscatter images taken from 1978 with 1996 to look for changes. The yellow are small changes. The pink are large changes. Now, in the Andes, the snow changes from year to year, so we don't worry about that. This large pink dot up here is where the Brazilian government put in a dam across one of the tributaries of the Amazon near Manaus, Brazil, and created a huge reservoir. And of course, there's some changes due to flooding and things like that there. But these other areas represent places where deforestation is occurring, especially along the coast. This bright dot down in the lower right-hand corner near the coast is the city of Sao Paulo, Brazil. And it's bright because of that. Okay, we're running out of time, so I'm going to skip a few slides. Here we can look at it, seeing at one incidence angle versus another incidence angle. Again, we can see how wonderful the radar is. Because the nadir direction looks straight down, we see the river really well. it's brighter, and the forest is darker. We get a lot of volume backscatter from the rainforest. And we can see that when we look at an off-nadir angle in the scatterometers, we get a much brighter rainforest. We don't see the river quite as well. And we see a very large difference between the rainforest, where there's a lot of vegetation, and the savanna areas where we have less vegetation. And we could do vegetation classification. I'm going to skip this in the interest of time. Here is looking at Africa, where we can see the difference between how incidence angle at 14 gigahertz affects what we see. The 11-degree incidence angle allows us to see swamps and water underneath the jungle canopies down here very well. We see the bright backscatter from the scatterometer at a higher incidence angle, but the deserts stand out very differently. The signal goes into the sand, is absorbed, and so they show up dark at high incidence angles, whereas at low incidence angles, we see some information from the surface scattering of that. We found that we could actually determine not only the amount of moisture by looking at the backscatter in there, but we could also see the wind direction by looking at the permanent little ripples, the small waves created by sand dunes. Now, I want to return to the cold for a second just to talk about Greenland, which is the largest island in the world. It's covered with several kilometers of accumulated snow. In fact, the snow is accumulated so high that the center of Greenland never melts. So the snow up there is very dry. The weight of the snow is so heavy that it compresses down towards the edges, and that snow and ice flows off to the sides in glaciers where it melts. Well, as the altitude drops, weather systems come in during the summer and can melt part of the snow, which sometimes refreezes to create ice lenses, these little blobs of ice in the snow. And further down, the snow gets so wet, the melting is so intense, that it actually forms surface lakes and rivers and things like that. Okay? But backscatter for microwaves is very sensitive to the amount of water present. Well, dry snow, which is frozen water, is very transparent to microwaves, whereas wet snow or water reflects really, really well. So we can see that in the backscatter images. So I've created here a sequence of backscatter images of Greenland for several decades. And I've done what's known as an anomaly plot, where I look at the difference between the normal backscatter and the change from year to year. And we can see how Greenland is evolving or changing with time. Back in 1978, there wasn't as much melting, and so we see very dark around the outside. As we move forward in time, we start to see brighter events coming up. These are the result of melting and refreezing, okay? It melts more in modern times than it used to, and when it refreezes, there's more ice being created because of the melt, and so it's brighter, okay? On the other hand, there's also more accumulation, more snowfall piling up at higher altitudes. That makes that snow sort of starts to attenuate any ice that's below it. So paradoxically, the scatterometer data reveals that Greenland is melting more, but that raises, but the higher temperatures of the atmosphere also produce more humidity, which results in more snow and accumulation. So which is winning, more snow or more melt? The data clearly reveals that Greenland is melting. More importantly, it's melting faster now than it was even 10 years ago when this data was collected. Okay, so here is a combined C-band and Ku-band image of Greenland during the summer. Around the outside edges, it's melted, so it looks very dark. Then, as we move upslope, we have areas that have melted and are refrozen and are currently refrozen. That refrozen ice is very rough, and so it's brighter. And then up at the top, near the center, there is lots of snow and lots of snow accumulation. So it's brighter again. And we can watch the evolution as a function of time of these different areas, these different zones in Greenland, And that's what we saw in that first image that I showed you. So I have a time series of an example of a melt. In winter, it's bright along the edges. In summer, it melts. It makes the backscatter look dark, and then it refreezes. This is a really interesting research area. So all you students, PhD students looking for an interesting topic, studying melting in Greenland and Antarctica and the glaciers of the Himalayas, are really an interesting thing. So we've done some of this up in here. There's more to do. I don't have time to do it. I just want to show you one last thing where we look at the sea ice and the movement of sea ice around Antarctica. And my animations aren't working here, but we've talked a little bit about the sea ice there. Okay, we've reached the end of our time. I have some more slides that I could show, but I wanted to leave a little bit of time for questions. Let me show you one last picture. This is a sequence of images that show multi-year ice in white. The light blue, the cyan, it shows the extent of first-year ice at the peak of the winter. Okay, so from 2003 to 2009, as observed by QuickScat, the amount of perennial multi-year ice, the thick, really thick stuff, has gotten thinner. In other words, the ice caps are melting. Now, during the winter, they refreeze over, but it's thinner ice that melts more quickly in the summer. And the scatterometer data independently confirms that the climate really is changing in the hemisphere. And there's some beautiful pictures as we can sort of illustrate that. The OSCAT data is allowing us to continue this time series looking at this meltdown. Let me quit at that point and turn the time back over to Shiv. Thank you. Sally, any questions?
Yeah. Thank you so much, Dr. David. And we have a couple of questions. I would request all the participants to send in their questions using the question box on your GoToWebinar so that we can take up the questions. So I'll start with the first question. Apart from rain, land-sea contrast may also significantly affect the scatterometer's retrieved winds. Can you tell about the uncertainties associated with the scatterometer retrieved winds?
Okay, I didn't spend a lot of time specifically looking at the wind process because so much has been done. The scatterometer measurements are noisy. And because of the noise level, we get a backscatter that is variable. So if I go back to my wind slide, where I talk about the model function that relates the wind, we have to do the intersection of the solution for wind speed and direction for each one of the models. And near the ocean, it works pretty good. But the problem is the antenna side lobes that we use are much, the antennas we use have side lobes. And so we get the leakage of backscatter from one area to another. Over the ocean, that is not a strong effect. But over land or near ice, where the backscatter is much larger than the ocean backscatter, the signal in the side lobes of the antenna can be stronger than in the main lobe. And that contaminates it. So usually we throw away measurements too close to land. Some of the resolution enhancement processing that I do allows us to recover some of that information. But like I showed you in the Hawaii image, we still have to mask out areas too close to the land. Now, what we're really trying to do is this little picture here shows the relationship between backscatter and direction and wind speed. Given a particular backscatter measurement from one direction of my scatterometer, I can't solve uniquely for wind speed and direction. So I take measurements from different directions of the same spot on the Earth's surface and solve for the possible solutions. The problem is, this is not a function. It's not invertible. And so even though I may have multiple directions, I run into the problem of several solutions for the wind speed direction. And I have to choose one. We call that ambiguity selection. And that's a process that's not fully solved. It's a great research problem for students. We've got some neat techniques that work pretty well, but it's not a perfect problem, especially in typhoon conditions. Not a good answer, but hopefully it helps.
Okay, thank you. Now, the second question is, what is the angle generally used of inclination for observations of a scatterometer?
Good question. We talked about a little about the relationship of incidence angle and the backscatter. There's a trade-off here. This is a classic engineering trade-off. This is a picture of the sea wind scatterometer, and the OSCAT, the Indian scatterometer, the ocean scatterometer, is very similar in geometry. So I have an antenna that's spinning around looking off to the sides. I could change the tilt of the antenna, and that changes the incidence angle. Okay, but the problem is, if I make it too steep, my swath width is narrower. So, but if I make it too wide, the backscatter falls off with incidence angle, and my signal to noise ratio gets worse. Both both the sea wind scatterometer, quick scat, and the ocean scatterometers use two incidence angles, an inner beam, this pink, and an outer beam, that's blue. The inner beam is about 46 degrees incidence angle. It's 46 to 48. OSCAT uses 48, QuickSat uses 46. The outer beam is 54 degrees incidence angle for QuickScat and 56 degrees for the Indian scatterometer. The difference between those two incidence angles isn't very large. It doesn't have much, that doesn't matter very much. But the wider incidence angle of the Indian scatterometer gives us a broader swath, which is nice, okay? So we usually operate in the very high incidence angle. Now, if I go to the scatterometers that I showed earlier, like that use the fan beam scatterometers, in the oops, I went the wrong direction. Anyway, they have a variable incidence angle. So they go from about 20 degrees incidence angle out to 56 or 60 degrees incidence angle. So I'm trying to pull that picture up. Next question.
The next question is, does the ice density affect the response of backscattering, specifically for snow density?
Yes. Microwave signals respond best to objects that are larger than the wavelength. Okay? So if I had a big giant crystal, it would bounce, the microwaves would bounce off really big. But snow crystals are very small. So you don't get a lot of scattering from them. That's the reason why snow is generally low backscatter. However, there are lots and lots and lots of snow crystals that are piled up. So if I have a snowpack and it's not very dense, there's not so many crystals. So I do not get much scattering. As I pack more crystals in, okay, same level, but maybe more crystals in, so it's denser, there are more crystals to bounce off, so I get more backscatter. Further, as I densify, make the snow more dense, then the crystals tend to get bigger. And in fact, if you look at Antarctica and you watch from one year to another, the level of the backscatter, I didn't get a chance to talk about this, but the level of the backscatter starts out low at the beginning of the winter and then gets larger through the winter until it starts to melt. The backscatter falls off and then it refreezes and comes back up. Well, the reason the snow changes the backscatter is because it's getting denser. The crystals are getting larger. Now, sometimes during the winter, that backscatter falls because we have more snow being piled onto it, and it's less dense, the snow on top. And so we see both increasing backscatter with time due to densification and decreasing due to more accumulation. Complicated answer because the geophysics are complicated.
Okay, There's a very good question. Which fusion technique is best to fuse optic and SAR data sets?
That is a great question. And you know what? I don't know the answer. Why? Because I don't think any of them are any good. I think we haven't figured the answer to that question out. I think there are lots of techniques and we don't have the right answer yet.
All right. Scope and advantage of higher frequency scatterometer like Ka band?
Okay, this is a really good question, okay? And the answer is very long, okay? Low frequency scatterometers like C-band, 5.4 gigahertz, have wavelengths like 10 centimeters. They penetrate through rain really well, but they're not as sensitive to the small waves on the surface because they are resonant with big waves. As we go to higher frequencies, shorter wavelengths, we are more sensitive to the small waves on the surface, which are more sensitive to the wind. So we get greater modulation. We get better wind at the expense of much more sensitivity to rain. In other words, Ka band can't be used in raining conditions at all. It's almost useless, okay? The other issue is a long wavelength, in order to get a small footprint on the Earth's surface, requires a big antenna. A short wavelength can use a much smaller antenna. A much smaller antenna is easier to put on a spacecraft. So there's a trade-off here. Do I want really good rain insensitivity, maybe a little more noisy wind, or do I want really good wind sensitivity, but I don't work at all in rain? So Ka band is an interesting new technique that's been proposed for several scatterometers, but I think in the end, we're going to have dual frequency scatterometers, two of them, low and high. I think Ka band by itself will not work as well as we would like. It's not useful in typhoons, in the monsoons.
Okay, just to follow up on this question, we have, so the combination of C and Ka band will be good option to use?
I think so, yes. I think the combination, the best. I showed you some land ice pictures of that, and you can see how there's more data when you combine them. But that's true over the ocean as well, even more so. Low frequencies, no rain effects. High frequencies, better sensitivity to direction, better low wind speed accuracy. In fact, to quantify that more carefully, ASCAT cannot accurately measure wind speeds less than 5 meters per second. At Ku band, we can go down to 2 to 3 meters per second. It's more accurate at low wind speed.
Thank you. So next
Which is why I
question
think
is,
the Indians use Ku band.
is it possible to detect water under the ice using radar?
Yes, it is. Okay, and in fact, we're doing that now. One of the research projects that I'm working on right now, we are using L-band radar data to image liquid water contained permanently in Greenland, Antarctica. It's ice that water that never freezes. It's called an aquifer. And those aquifers are something we just recently discovered as in the last couple of years. And they're actually really important to melting. We didn't even know they were there, but these reservoirs of liquid water means that the ice is warmer than we thought it was, which means it'll melt much faster, which may be one of the reasons Greenland is melting so much faster. So yes, radar will work very well because as it penetrates the ground, there's not a lot of reflection from ice, but as soon as you hit water, you get a huge reflection, and the surface of that water tends to be very rough and therefore easy to see. Now, gotta have the right frequency. Short wavelengths don't penetrate as far because a lot of reflection from the snow. Long wavelengths penetrate a long way because the ice crystals, the snow crystals, are smaller. Tricky problem. Good question.
So I think I'll just take the last question.
Okay.
In your opinion, what should the optimum spatial resolution for future scatterometers be to serve maximum number of applications provided by them? So what should be the best achievable radiometric accuracy?
Okay, there were two questions there. One was spatial resolution. The other one was radiometric resolution, which means noise. Okay,
Yeah.
you're talking to the guy who's pushing for high resolution scatterometers. And I'll tell you why. A lot of really important geophysical effects occur at the 1, 2, and 3 kilometer resolution. Ultimately, I think we're going to need scatterometers that operate to 5 kilometer resolution and better in order to do the best thing that we can do. So I think that ultimately we're going to need these fine resolution scatterometers to better resolve rainfall, because rainfall is a very small event. We think of it as a great big huge, the monsoon is huge, and it's true, but rain falls in cells, small chunks at a time. Those cells are typically 1 to 2 kilometers in size, and then there's one behind the other. And in order to resolve that, we're going to have a scatterometer that operates at finer resolution than that, but still provides very wide swaths. Now, for noise resolution, KP, the effective noise resolution needs to be of the order of 1/10 of a dB or better, or if you want to think about it that way, better than 1%. Right now, the resolution is somewhere between 2 and 3% for the Indian scatterometer, and a little worse for ASCAT. But we need to get down to below 1% in order to do this. Why do I say that value? Because it's the calibration that's the most important thing. And when we make an observation, if I want to make an accurate wind measurement, or an accurate snow measurement, or an accurate ice measurement, I need to know it to a few tenths of a dB, 1/10 of a dB accuracy long term. Well, I can do some averaging, but for very rapid events, I want to get it as accurate as I can. That implies that we need a little bit more transmit power to have higher signal noise ratio, and a little bit bigger antennas to get finer resolution. And those two together can give us both better radiometric accuracy and better spatial accuracy. So that's my big push. I'm hoping it will move ahead on that. And I've been working with making proposals to improve both of those, both spatial and temporal resolution. The other thing that we want to look at in the future is trying to measure both wind and ocean currents at the same time. And a scatterometer can do that if we use the coherent signal idea. I could go on for a very long time, and you probably don't want me to do that, so I'll stop there.
Thank you.
Okay, thank you. Thank you. Yeah, you want to say?
No, sir. I was going to invite you to do the vote of thanks.
Okay, let me thank Dr. David Long for a very special and extremely knowledgeable to many of us, and to your knowledge, because participants are not visible. There are more than I think about 75 participants from 40 countries. So you are not only heard in India, but other countries also from this platform. So it's a new normal where the people from different countries can our program. So it's a very good thing. And I'm happy to know that many of the questions are very good at very high level, and certainly it shows that you have conveyed what you have done and what are the prospects of future scatterometry, including multi-frequency and including the measurement of depth, measurement of water below the ice. So with these words, I thank you again for coming to us and shared your knowledge with all of us. Thank you very much.
Thank you. I appreciate everyone attending, and I hope you found something useful to think about.
Okay, thanks. Bye to all, and close. Bye.
Thank you, Shally, for organizing this and arranging all the details.